Today we are going to talk about where we left in the last class. If you want to develop a AI-based system for game playing, so in the game playing, what is going to happen that let's assume that a simple setting where two players are there. So first you would be doing something, then the opponent is going to do the something, and your objective would be to maximize the profit. Let's assume that because at the end you want to win. So let's assume that by winning you get 1 point. So your objective would be to get 1 point, but let's assume that by losing you get 0 point. So when you play a move, the opponent would try to minimize your thing in his chance because he want to win. How can he win? He can only win if you lose. So he wanted to minimize that profit that you have. So there is a someone who is max, there is someone who min. Who is max? You are max. Okay, you are max, and who is min? The system is min. Who is actually going to uh, come in to defeat you? However, if the system is playing, for example, if you are making a AlphaGo kind of system, then you want that system to win. So, the system to which you want to be system to which you want to win is going to be called max, and the another system is min system. So objective is this that min in all available choices picks the particular move which actually minimizes your profit. So we have seen in the last class that this is a kind of tree that actually connects all the possible ways that in which you can actually proceed. And this is with respect to tic-tac-toe game, where initially it's a very simple game. Everybody knows this, that there are 9 squares, and if Max is allowed to go, so he can put a X at any point of at any place. So how many places he can put the X? 9 places he can put. Okay, and then it is a chance of Max. So min would put 0. So with respect to every allocation, he can put 8 places, so 0. And then again, it is a chance of max, so he can put X anywhere. So this tree proceeds in this particular way. You know that there are 9 different layers. So factorial 9 number of nodes are going to be generated, and you can see that this is going to be a huge number of nodes which are actually possible. So this is very simple game, but you can see that the number of ways in which the things can proceed, uh, uh, number of outputs are going to be factorial 9. However, you can see that many of them are going to be repeated. Okay, in the different way also you can reach to them. So there would be multiple repetition, but this is a huge number of things that are actually we have. So it is not it may not be possible for anybody to win in a particular way. For example, if he says that I am going to put X here and then X here, then X here, then by this I can make this particular line. Okay, he can also think in this particular way. This is not possible. If you can come up with this kind of a strategy, playing this tic-tac-toe game, you would not be able to win. Why? Because if your opponent would be definitely in putting something in your way, and you would not be going to forward. You would not be able to proceed in that particular way in which you are thinking. So a particular way of finding answer may not be possible for you. However, it is always possible that if you learn a kind of a strategy, then you can utilize that particular thing better. So a strategy is needed instead of a plan. It's just a kind of winning states. It is not possible. Okay. So we have seen this that in the last class also we have discussed this thing is a little bit that apply means the game moves in a dual manner. So one would be your turn and opponent turn, and then it becomes one ply, and after that the same two things are going to be there. So in one ply, since you have multiple options to go, so a1 a2, let's assume that these three actions you can take. Let's assume a1 a2 a3, three actions you can take. So each with respect to the every actions, main also can take some action. Let's assume b1 b2 b3 actions he can take. So this complete tree is actually kind of one ply. Okay, it is not like that you think that from here you go here, then you go here. It is not like that. Somebody else is going to act on the second level, and that's why the one your one move is going to represent this particular part. We call it lie. Make sense? So in the game playing situations, the solution is extracted using something called the min-max method. So what is the min-max method? So max is trying to maximize what he can get based on the minimums that can be provided by the mins. He wanted to maximize his sim based on what? Based on the things which min is going to give. For example, if he takes action A1, then it is a chance of min. Let's assume that the three things are not not possible. You take the print screen and put it one by one. 20-30 होंगे बस. Okay. So so this so if you take the action A1, you come here, and from here you actually it is a now the min can take these three options. Out of them, if the min takes B1, you get the profit of 3. If the min takes B2 actions, you get the profit of 12. If min takes B3 action, let's assume these three actions are available, then you get the 8 profit. Let's assume that somehow it has been computed. So can you tell me that what is the action min would take? B1, B2, B3. Which action he is going to take? I'm sorry, I cannot read your comments right now. Can you please
Even
speak? B1?
should
Yeah, because he want to minimize it. See, he don't want to give you much profit. So he would take this particular action. So here, when you are sitting here, you can think that if you take this action, you what maximum you can get is 3 only. In the same way, if you take the A2 action, then min has 3 choices: C1, C2, C3. In the if min takes C1, it gives give you 2. It's C2, it gives you 4. It's C3, it gives you 6. Okay. So again the same question I'm going to ask, that what the min would take, C1 or C2 or C3?
even the minimum one.
The minimum one, this action, so that you get the minimum one, C2. So by this you would be getting 2. So from the top level, if you think that going in this particular direction, I get the profit of 3, and in this direction, I got the profit of, I'm going to expect the profit as 2. So would you like to explore the possibility that what would happen with the C2 or C3? I'm asking a different question. So at the time of when you are here, you are going to take this particular action. At this time, how much profit you are going to get, because system is going to ultimately find out these numbers. Okay, how can you get this 3, 12, and 8? It is not written anywhere. You have to explore the tree to find out that what is the goodness of this particular move and etc. So you expanded this and find out 3, you expanded this, find out 12, you expanded this, find out 8, and after that you have decided that here that okay, if I take this action I would be getting 3. So while evaluating this particular move, when you came here, at that time you evaluated this particular move and find out the value is 2. So you understood that since 2 is less than this 3, so whatever here is, you would be definitely getting less than 2. 2 or less than 2, because you got the value 2 na. So min is not going to give you anything more than 2, whatever value here. If here the value is 1, so you would be getting 1. But if the value is 4 or 6, you would not be given any that particular road where you can get more than 2. Am I making sense? So it means that you the point when you encounter this particular 2, you need not to explore this tree further. Is a very important point. The point you actually encountered this true, you are not going to explore this 4 and 6. Why? Because you know that min is going to give you at least 2, at most 2, sorry, at most 2. And here you have a chance to get 3. So why would you go into this particular direction? Okay. So what I was telling that at this particular at this particular place, you are thinking that three things are actually possible. Out of this, you evaluated all these things and expanded all the tree and find out that the value is three is the maximum thing that you can get. So when you came here, you find out the value two, then you need not to explore it because you know that whatever it comes over here, he is going to give me two is only two. And why 2 is important? Because 2 is less than 3. If it is less than 3, why you would take this particular option? You would not go into this particular direction. By having this kind of understanding, after having this kind of understanding, you can immediately tell that I'm not going to explore this and this. This you have explored because when you came into this particular direction, you have to explore this particular place. But these 4 and 6 you are not going to explore. In the same way, if because here also you go because three actions are there, two actions you have actually evaluated, you go to the third actions, and in this particular action, if you find out that 14, okay, you become happy, okay, I can get this 14. Because if all other values are greater than 14, then max min is bound to give me this 14 this particular way. So, but next one is 5. So again, it becomes a problematic, but still I am hopeful that 5 is actually greater than this particular 3. So I can think that, okay, I can get more profit. So I'm going to explore this also. And by chance, if I get 2 over here, so again, everything is collapsed. I say that, okay, if I go into this particular direction, min is going to give me 2 only. So this is not a good idea. So let me go into this particular direction. So this is how the things can proceed. What is important thing is this, that if you follow this particular methodology, so you need not to explore this particular part. And here who was telling that the things are arranged in this particular way, that they are 14 5 and 2. It may also be possible that they are arranged in the 14 2 and 5. Then whenever you hit the first two and it is less than 3, you say that I'm not going to explore this particular part. So you are expecting actually that it is because this is the worst case setting. Now the best case setting would be 2 14 and 5. The second best case would be 5 2 and 14, and third base, this is the worst case setting. So out of these three, so you can see that 1 by 3 it is only 1 by 3 probability that you would be expanding all these things. So what we expect that in most of the cases we are going to get some kind of profit. Okay, so this is a standard method that we can utilize to not explore some of the things. So this is called the min-max setting, where I'm telling that if you are at any particular point, so this, let me just tell you that what it is. It is telling that terminal test, if you are at the final state, then whatever value, utility means whatever value you have, you say that this much is the only thing that I can get. But if you are a max player, you are here, so you evaluate all these places and try to see the other person, what the other person is going to give you, what what the other person is going to give you. Okay, what maximum he is going to give you. Based on that, you can you maximize this particular quantity for all the available action. These are the three action for which you are going to find out. If you are a min one, if you are here, then you want to find out that I am going to minimize this particular value for taking all these action on my stays, and then I can decide that what action, the action which actually maximizes or minimizes, I'm going to tell that take this particular action for this particular state. Hope it is clear that how to take the actions. Okay, the same thing is written over here. It is a min-max algorithm. So So what essentially we got with this particular method, that is called the alpha beta pruning, that tells that you need not to explore the idea that if here the value is 3 and here in this particular tree if you get 2, then you need not to explore this particular part. This idea is called the alpha beta pruning. It is a standard algorithm that tells that you need not to explore further. By this, what happens now? Earlier, what was happening, that uh, if the branching factor was b, then it says that you are actually going to have b to the power, if earlier your complexity was order of b to the power m, now your complexity would be b to the power m by 2, because half of the items you expect that you are not going to expand. Mathematically, this represent what? That you can say that b to the half to the power m, if you represent the same thing into the same framework. So b to the half becomes under root b to the power m order of this. So earlier things were b to the power m, and here now the things becomes under root b to the power m, means your branching factor reduces from b to under root b kind of thing. So it becomes very good algorithm to go ahead, and finding out the solution becomes very easy. Okay, so we have this thing we have actually already seen, that this is called the alpha beta pruning. Okay, so it actually says that you are going to maintain that you are going to maintain the value of two parameter which are alpha and beta, and this algorithm goes in this particular way that initially you are telling that what profit you can get, that is alpha, what the other person can give you is beta. So you say that let's assume that minus infinite no profit I have. So you go into this particular direction, you take this particular action, and you actually discover that there is something that gives you 12, 3. So here you put 3 because 3 is the min wanted to give, because only one value is there. When you expanded second one, it is 12, but it is greater than the 3. So you are not going to update this particular place. It again remains the 3. And the third one, when it also comes, then again you are going to get 3 only. You are not updating this particular value because this is the minimum one. And at the end, when everything is completed, you say that the 3 is the minimum one that I'm going to give to somebody. And then this value comes here. And then you start exploring the next path. In the next path, you find out 2. So you put 2 over here. And when you put 2 over here, and this is actually lesser than this, the algorithm says that I'm not going to explore further. It comes back and explore this particular portion, explore this, find out 14, explore this, make it 14 becomes 5, explore this, 14 becomes 2, and then this 2 comes over here, that this is you are going to return over the system, but the same value is not updated over here because you know that why you would take 2, you would take the 3 because 3 is a better value. So you take this particular value and you go into this particular direction. This is important algorithm, and as we have understood that it takes it only examines lesser number of nodes. Okay. Uh, However, when the successor are examined into the random order, it needs to examine only order of b to the power 3m by 4. So this is the best case, na? If the perfect ordering is there, every time you are going to neglect the things, then this is what you are going to get. But in practical, actually, you are going to assume achieve this much. So b to the out from of b to the power m, you are going to get order of b to the power 3m by 4. How come b to the power 3 by 4? So actually, this is a kind of idea that so actually, if I ask you that, let's assume that you have a stick of 1 meter, okay, and when you drop it at the floor, it breaks in two parts. Let's assume that you have a stick of 1 meter. When you drop it on the floor, it breaks into two parts. And let's assume that it breaks at any point at any place randomly. Okay. Then my question is that what is expected? What is expected? What is expected number length of smaller portion? Can you tell me what is the expected length of smaller portion? Whether the question is clear?
Yeah.
Okay, so you have a rod of you have a let's glass rod of 1 meter, and when you drop it on the floor, it is going to break into two parts. And let's assume that every time it is going to break in two parts only, and it is going to be random only. I want to find out what is the expected length of a smaller portion. So now you can think that since I'm going to every time take the smaller portion, so a smaller portion would be less than half. So actually randomness, which was actually earlier you were thinking is going to be on the complete thing, is actually randomness in this half part only. So so expected value is going to be 1 by 4. 1 by 4. So using same kind of concept, this formula is derived. I'm not going to that much detail, but I just wanted to give you high level understanding. So this method can make your algorithm faster. Alpha beta pruning make your algorithm faster, and you can get the result into the better way. In the chess, for example, especially if you just consider the chess thing, in the chess, a strategy that can, for example, use this thing capture, three, forward, and backward means if possible you capture something on the if in the game of chess, if possible you immediately capture. If not possible to capture anything, then provide something so that the opponent is into the miserable situation. There is some checkmate or whatever there is a, so you try to threat him. If it is also not possible, you forward your things, and if no forwarding is also possible, then you take your things backward. If you use this particular strategy, so this is also going to be a better strategy. Gets you with the about a factor of 2 for the best cases. So it is also a very good strategy. Another strategy when you are deciding, let's assume that when you are making a game of chess, could be that try first you know that there are some books and people keep writing that what is the way to go ahead and good into the uh, into the chess. So there are few initial moves. I'm not sure that how much you know about the things, but it happens that there is a, if you move this thing, then you move this thing 3 points, then after you put the horse over, then after that you can kill this thing, something like that. So there are few setup killer moves are there. Set of moves that are called the killer moves. If you go with them, then you are more likely to win. So you try and tested method. So you use those things to initially attack. Okay. Another method could be that you can, when you are developing this system, that iterative deepening could help. So what do I mean by this? That you know that game of chess goes very deep, 60-40 applies. So you say that initially I would only consider 10 thing only. Whatever is best, I can use that particular value to give the solution. This is another way to make your thing happen. One also a very important thing sometimes is needed is the hash based previously seen positions. Means what happens now, especially into the chess kind of game, you have seen that sometime you forward something and then do something and after do something and after that what happens, you reach to the same board position. It happens or not? Sometimes it may be possible that you are taking some moves and after that you are reaching to the same board position. So this is not a good idea, because what if you are reaching onto the same board position, then your algorithm is again going to suggest you that go into this particular direction only, because based on the previous thing, it is again going to do the same thing. So you are going to stuck into a circular kind of motion, and or let's assume that opponent is also going to take the similar kind of move, so you are stuck. So this to prevent this particular scenario, you can utilize a table that you can call it a transposition table, where you are going to put the hashes of the board positions. So whenever you are going to take a move, you just consult this, that whether I have gone this particular place earlier or not. If you have gone this particular thing earlier, don't take that particular move. Okay. So so this is actually very much important, that we have to cut off the search earlier. As I mentioned here, that the game can go much deeper, and by this, if you try to find out the best move, you would not be able to do that. So it is better to use the some cutoff value by which you can say that I am going to stop at this particular motion position. And if you want to stop that is a particular position, then there becomes a very important question. How can you tell that which particular move is better? Any idea? So my question is this: that let's assume that this you are on this particular board position, and then you did something, and finally you reach to this particular position. So standard way is this: that you see that if I do this and another person do this, then do this, then after that I am going to either win or lose, win or lose. Okay, this is going to be the last layer. And then by this you find out that okay, looks like that this is a better strategy. I am going to go into this particular direction. Am I right or not? So initially you start from in zero board position or whatever board position you are in, then you find out to complete list till you get a winning or losing. And if you are winning, you are going to take that particular path only, and you suggest that I'm going to forward into this particular way. But as I told you, that number of nodes in leaves is actually very large, and therefore it's not possible for anybody to enumerate all these situations. So the better solution is that you stop somewhere earlier. Yes or no? It would be a better solution, because if you try to go deep down, it may be infinitely time. So after having a move, the opponent may take infinite time to come back to you that what I should give you. Am I right or not? Hmm? If you consider everything, it may take infinite time to come back to you. Yes or no? Is there anyone?
Yeah.
Yes.
Yes, sir.
Yes. So so what to do? So what is the problem in this? The problem is this, that if I make the system like this, I would not be able to give make the system. So what is the solution? So what is the solution? One solution is you stop at this particular depth. You don't go beyond this particular depth. Okay. So you can use iterative deepening kind of thing. You can tell that I would go to particular D depth only. Will this be useful? Will this be useful? Yes, it will be useful because ultimately it is going to give you some answer. Na? I'm not sure that it is the best answer or not, but it will give you some answer, because game must proceed. If the game is not proceeding, that is a big issue. Am I right or not?
But we can have only three results, sir, in any game: lose, win, or draw.
Okay. Yes. But this would come when you go to this particular depth. Okay. But if
Uh,
you start going to this particular depth, number of leaves are very large, and it may be possible that you may not be able to enumerate all of them, and therefore you would not be create this particular system. So my problem is this, that number of things which are here are very large, and that's why I cannot enumerate all of them. So what should be the way around? One way around is this, that you say that I am not going to consider everything. I am going to only consider the theft. My question is, does it make sense?
Not in real world, I guess.
Okay. Okay. So one at least it solve one problem, that it can give you the answer. If you go to the complete depth, you may not be able to give the answer, as I'm telling. So if you restrict your depth, then at least it ensures that the game would be forwarding.
Yup. Up to certain extent, yes.
Yes, na? Because if I say that if you explore this much, you're not going to give me the answer. So if I say that restrict to here, so definitely it solves this particular purpose, that you would be able to find out the answer. This part. Now there is another part which says that I should win also. Na? Why I'm playing? I'm playing to win. But whether I would be win by this strategy, I'm not talking about that right now. Yes or no?
Yes.
I may not be able to win. Why I would not be able to win by this? Because the actual winning and losing comes when you go to this particular depth. If you are stopping at this particular depth, how do you know that whether you are which move is better? Am I right or not?
But again, in that stage, it is incomplete, right, sir?
It is incomplete, but that's why I don't know that whether it is right or not wrong. If I don't know that which is right and wrong, then out of available choices, how can I tell that I'm going to take this particular direction? Do you agree with me? Once again, let me tell you, I don't want to, let me go once again from zero. So what I was telling that I had a chessboard position where I wanted to find out what should be my next move. So the system says that if you take d depth, then you would be able to find out that what is the whether the game you are win or loss. So there are multiple choices now. There are multiple choices that you can take at this particular place. For everything you evaluate that if I take this move, I take this move, I take this move, whether I'm going to win or lose, win or lose, win or lose. So you have to go to this particular depth. Let me call it capital D to this particular depth. But going to this particular depth is actually very very difficult because it is very large number. So you what you do generally you go there is one solution that I'm going to tell is you stop at this particular place. Okay, you say that I'm not going to go beyond this particular depth. Okay, so if I say this, I definitely have one improvement that now my system would be uh, my system would be able to give the answer because this depth my system was not able to give the answer. Now I can give the answer. But the issue is that since the game has not completed at this particular moment, so I don't know that whether this is good or this is good. This is my problem. Do you understand my problem?
Yes. The point where we need to stop, it's kind of a risk free. If we go beyond that point, then anything can happen. That is the assurance we have if we are stopping there.
Hmm. But this if I can give you the assurance means what I know something about the game. If I have this information, then I
Yes,
also know
of
that
course.
whether I'm going to win or lose. So so this information is not with me. Okay, this information would only be with me if I go further deep down. Then only I can know that whether I'm going to win or lose. So at this place, this information is not there. So this is the biggest issue that if I don't know this thing, I cannot decide that which move I should take. Everybody is agreeing on that. Okay. So what to do? So the solution could be that find out some methods that can tell you that how good this particular board position is. Because from here you are going to move to this particular board position. Is there any way to tell that how good this particular board position is? Is there a way to tell? I'm not sure about this, but you know that if there is a board position where there is you know that there is a queen. Okay, he can move in all the direction. Okay, wazir or move. He can move in all the direction. If you have a board position where you don't have wazir and there is another board position where you have wazir, so which has the higher value? Definitely the one which has the wazir. Similarly, if you have a you have a pawn, so two having two pawn or having three pawn or having four pawn, so which is better? So maybe some kind of heuristics you can apply, and by this you can tell that however I don't know that what is the final answer is whether the person is going to win or lose, but I can tell that this board position is better than the another one. Yes. And this information can be utilized to tell that looks like that this particular direction is more promising as the another one. And then you can utilize this to take the right kind of actions. Am I able to convey this? So what I wanted to tell that you want to develop a evaluation function that can tell that how good this particular board position is. If your board position is good, then you are most likely to get win. So this function should be such that if you give any win and try to evaluate, it should be greater than the try to lose, and draw should be in between the value. One such example, for as I told you, that we can use features from the board position, such as how many number of pawns are there, how many number of queens are there, etc. And we can have various categories. Suppose that the experience suggests that 72% of the states encounter in two pawn versus one pawn category lead to win. 72% of the cases, when you have two pawns, you are going to win, and 20% cases you are going to lose, and 8% cases you are going to draw. So you can draw a evaluation function because 72% you are going to win, so you are going to get the number 1. 22%, 20% you are going to lose, so you are going to get 0. 8% you are going to draw, so you are going to get half the number. You can say that that particular board position, you can assign this number 0.76. Am I right? So using two pawns, you can find out a number. Similarly, you with different kind of functions, you can find out a different kind of number. Different kind of features, you can find out different kind of number. And then you can develop a weighting strategy on that, and then by this you can come up on a function that can serve the purpose of your evaluation function. So you can build a evaluation function in this particular way that can solve your problem to give your answer. Once again, what was the problem? That I was not able to give the answer because number of explorations that I have to do is very large. So what I did, I have restricted my exploration to a particular depth, and I told that I would not explore anything beyond this particular depth. I told that I would not explore anything beyond this particular depth. Okay, so that I can give the answer. In that scenario, I would be stuck in a problem that I don't know that whether this particular position is how good this particular position is. To tackle this particular position, we can use some kind of features, and these features can help me to find out a evaluation function. And this evaluation function, by using this particular evaluation function, I can decide that what should be my next move. Okay, so there are multiple considerations when you are actually developing these things. So one, just now we have talked about, this was the cutting off search, that to give the solution, we can cut off the search. But another idea could be that when in the game, what happens now? Let's assume that these are the moves you are going on. So initially what happens now is everybody gives a kind of things, then some person other does the same thing. So initially not much action is happening. Okay, do you understand this? Initially what happens now? When you are going to play game of chess, you are just forwarding your pawn. He is also forwarding his pawn. Then you are going to take out your horse. He is going to also take out the horse. Something is happening. It is not very actionable. But after a few minutes, what happens? Everything is set up over here. Now, lot of action is happening. Okay. After few minutes, again the similar kind of things would happen. That not less, not much action is going to happen. After that, then again there is a actionable time. Then again something routine happens, something like that. So one consideration is this, that instead of saying that I would explore the things to the D depth, you go to the point where there is an action is going to stop. And this is called the quiescent state, and you go to that particular state only. And then you can find out, it would be a better idea to determine that what should be the next move. Okay, yes or no? Uh, Forward pruning actually says that look what happens now when you are actually playing. So there are multiple options available. So what I wanted to tell that everywhere there are multiple options, but we have something in our mind. That's why we don't explore all the things. We go into this a particular kind of direction and want to play the game like this. Have you seen this? When you are playing a game, something comes in your mind. This drives your force, and you actually play into that particular direction only. Multiple options are there. You sometimes you don't go and explore all the possibilities. Okay, this is called the beam search. So you have some beams, you have some idea that I go into this particular direction, you go into this particular way only. And so this says that you are cutting out some many of the search without evaluating them. However, this is not a good idea. This may be fatal, this may be wrong, but sometimes it happens. You must consider that whether you are going to do the beam search or not. Okay. And another idea is search versus lookup. And this is also a very important thing. What happens that you know that in the game of chess, very big peoples have actually played the games. Grandmasters have played the game. So what happens that they also have been in this board position scenario. And what was their move? What move they have taken? If this was the board position, what move they have taken? If this was the board position, what move they have taken? So if I maintain this particular list, so I can do a lookup also. So I need not to go into the search because search is going to take a lot of time. If this kind of table is already available to me, I can just look up and find out that what is the good move for me and I can proceed. This could also be a good idea. Yes, yes or no? So all these things are important. So I would just stop at this particular moment to tell that these are the important criterias. So to when you are going to develop a game-based systems, okay, where there are two players and you are going to exchange your turns and find out the solutions. Now I'm going to talk something different. And to go to this particular point, I just wanted to invite any questions if you have. Once again, let me tell you that what we have seen in this particular session till now. So what we have seen that using alpha beta pruning and using cutting up the search, there is a possibility to make the system efficient. Okay. However, there are some issues. To fight out with these issues, we have seen that you can maintain that what were the good things earlier. You try to go to the quiescent state and then find out that what is the best move. So there are some ways in which we can improve this kind of searching mechanism and we can build this game-based systems. And this is the point that I wanted to make. Hope it is clear to everybody. Yes,
Clear, sir.
clear. Next thing I wanted to discuss is the constraint satisfaction problems. So this is a new thing, okay? Everybody, I invite you to please start thinking once again. And if you have any questions, please ask and participate. Okay. So constant satisfaction is this sometime we want to find out because it's an intelligent task. Na? In the intelligent task, we want to find out something, some answers. So let's assume that there are some variables, set of variables such as x1, x2, let me call it x1, x2, xn, and they can take the values from this particular domain d1, d2, d3, d4, dn, and they have the domain. It may be possible that their domain is same. For example, if I say that x and y, these are the two variables and their domain is say 1, 2, 3, 4. Okay, x can take these four values, y is 5, 6, 7, 8, 9. Okay, let's assume these are the things. And I say, and then I have to specify, and there are some constraints. Constraint is this that 2x plus 1 is equal to y. If I say like this, okay, if I put this constraint, it is a equality constraint. I can also say that 2x plus y is greater than y, let's assume that this is the non-inequality constants. So I can put various kind of constants. So if I put this kind of constant, so can you give me any solution? Can you give me what is the value of x? What is the value of y? Can you give me a solution? 2x plus y is greater than y. So can you give me any y? So let me take the minimum y as 5. So if I take 4, so it is 9. If I take x is equal to 3, so how much it is? So am I satisfying the constant?
Yes.
है ना? You can find out multiple solutions. It is not in this particular case. You know that there are multiple solutions. You can here you can instead of 3 you can also put 4 with 5. So if I put y is equal to 6, so multiple solutions are there. Okay, multiple solution is possible. That is not a big problem. So this is the constraint satisfaction problem. Okay, here we have what set of variable, set of domains, and set of constants. And sometimes people say that you can write like this, such as x1, x2. What are the variables and what is the function? Something like you can write like this. So to solve the constant, this is called the constant satisfaction problem. So what is the problem? Find out the values too of x and y. So this is called the constant satisfaction problem, and it needs the state space and the notion of the solution. And what is the solution? Means when everything is correct. So here, if I want to find out the solution into the search, so how many states are possible? For every value of x, I can combine, for example, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 2, 5, 2, 6. I can create so many states. How many states? 1, 2, 3, 1, 2, 3, 4, 4 multiplied by 1, 2, 3, 4, 5. 20 different states I can create. For each of these states, I see that whether they are going to satisfy the constants or not, and then I can by this I can tell that which is the solution. Okay. So the solution is actually called consistent. If I find out the solution, means I can find out this particular x is equal to 3 and this solution, this is consistent. Okay, consistent means whatever this particular condition was, whatever this condition was, this condition is satisfied. So that's why I say what? That it is consistent. So so this x is equal to 5, x is equal to 3, and y is equal to 5 is assignment. If I say that as x is equal to 3, so it is partial assignment. Na? Complete assignment is not there. So generally our idea would be to find out the complete assignment that is consistent. So hope everything is clear. It's very simple, na? No problem in that. Any problem? Yes. There's any problem? No.
No.
Okay. Good. Now I have a problem for you. So the problem is called the graph coloring, map coloring. So I have a map. This is the map of Australia. I have never gone to this place, but if you have gone, please correct me that if I am wrong. This is the map of Australia. So this is Western Australia. This is Northern Territory. This is South Australia. This is Queensland, New South Wales. This is Victoria, and this is Tasmania. These all things makes the Australia. Now my objective is that I have 3 colors. How many? 3 colors. So I want to color them. So if I put red color over here, I cannot put red color here because what would happen that then they both of them would get merged. Na? I don't want this. So I cannot put the red again here. So I can put any other color such as blue. Then I can put here what I can say if I put blue over here. So here neither I can put R, neither I can put blue, Then I have to put green. So what color should here I should put? Again, this is a question, okay? So this is a simple graph, but if I have a bigger graph, you have to find out that what are the color. Again, this is the same kind of problems where we have variables. What is a variable? Variable here are the name of the cities such as WA, Northern Territory, Queensland, South Australia, New South Wales, Victoria, and Tasmania. These are the variables. These are the variables. And what is their domain? R, G, and B. These are the three values which are, and the domain is same for all of them. I can give the color to them. Yes or no? Say yes
Yes.
or no.
Yes.
And what are the constraints? Constraints are this that since if you say that WA is very near to NT, so I can say that WA is not equal to NT. This is one constant. Okay. WA is not equal to, so this because of conversion, na, this becomes wrong. So you can write constants. I'm just removing this. Can you tell me that? Help me to find out what are the constant. So this is WA and T, na? WA and TQ, and this particular list is here. This list is everybody's clear. Now let me write constants. Help me to write constants. So W. So one thing. Let me just tell you this thing from this particular graph map. I can create this graph. How come? Because WA and NT are nearby. When they are nearby, I just draw a line between them. SA and NT, there is a line. SA, Q and New South Wales and Victoria, all of them are connected. So how they are connected, I created this thing. Okay, any problem in this? No problem. Now let me write what are the constants. So the two values should not be same. Okay, WA is not equal to NT and T is not equal to SA and NT is not equal to Q. And similarly, I can write multiple things. So I ask that all of you can write this. So there is some problem because I have done the conversion now, because that's why it is not coming correct. So is it fine,
Yes.
students? Can you write this? All the constants. So I call all of you to please by yourself write these constants and then check on the PDF that is available on our course web page. So there you can find out that what is over there. So by this you can just verify your answer. There are many solutions to the problem. Am I right or not? Okay. So this graph is actually give me a better understanding of the problem. So how to solve this particular problem? My question is how to solve this particular problem. So this was the graph. Okay. So R, G, B, any value is possible. NT can also be RGB. Q is also R, G, B, R, G, B, R, G, B, R, G, B, R, G, B. All is possible. So once you, let's assume that you start solving the problem and tell that, because without lots of generality, you can assign any color to the anybody. Okay. First. So you, let's assume that you pick the essay and you assign the blue to that. Why you pick the essay? Because it has the most number of constants. So let me first satisfy him. If if independently I can supply something to him, it becomes very easy for me to consider all other things. So if I give him essay blue color, let's assume that I have given the blue color to the essay. I have given blue color to the essay. Then I cannot give the blue color to WA. I cannot give B color to NT. I cannot give B color to Q, B color to NSW, B color to V. Yes or no? Hmm?
Yeah.
Yes.
Yes.
Yes. This is called the constraint propagation. That I cannot do give the same thing to that. So here you can see that there were 5 things. So everybody can have 3 values. So 3 to the power 5 choices we had. If I'm considering only these 5 one, okay, 3 to the power 5 choices were there. That is 243. And now when I propagated this constraint to all of them, so I remove one of them, so it becomes 2 to the power 5. That is only 32. Can you see how strong this technique is? Constraint propagation. It is actually 87% of the reduction into the problem. Got the idea?
Yeah.
So this, I just wanted to tell this particular point. Question number 1, what is constraint propagation? So you understand that what is the constant propagation? What is the importance of constant propagation? You can see that this has, in this particular case, have reduced the effort by 87% straight away. Now you can apply anything to here. For example, if you give green over here, now you cannot give green to this particular fellow. So it becomes red. As long as it becomes red, you cannot give red here. You can give green. Constant you are propagating, you give green to heat here, it becomes red. Red, it can become green. You can see that immediately you can find out very easily what are the colors. And here Tasmania, whatever color you want to give, 3 different colors you can give. And by this you can come up to answer. Now let us see one more problem. And this is a crypto arithmetic puzzle where question is this, that TWO plus TWO is equal to how much? FOUR. Let's assume that this is what the crypto arithmetic question. And here our understanding is that let's assume that these characters, for example, T, W, O, F, U, R, they are coming from 0.9. They are a single digits. Okay. And let me say that there is a constraint called all diff. I say that all of them are different. Otherwise, you can say that put all these values to be 0. 0, 0, 0, 0, 0, 0 is equal to 0, 0, 0, 0. So let me tell that this is not allowed. All of them are actually different. All diff. So I say that. So do you understand the problem? You have to find out that what is the value of FOURTOW. What is these values? All different with all different numbers. So so I'm telling that these are the characters and they are all different. So how can I create the graph out of this? How can I create a graph out of this? To do that, I have to create some kind of mathematical understanding. This O and this O, they are added and then becomes R. So you know that whenever you are going to do some addition, there is some other word can also come. Maybe carry can also come. So you can write O plus O is equal to R plus 10 multiplied by C1. Am I right or not? Similarly, this W plus W plus C1 is equal to U plus maybe another carry C2, 10 multiplied by C2. Everybody, please you understand. Can you let me know that it is fine? These are the constants. Similarly here T plus T plus C2 is equal to how much? O plus maybe C3. One more thing. And then C3 is equal to F. you know that C3 is equal to F because whatever is there, it comes down. So you are creating F, T, U, V, U, W, R, and O, and then you are connecting them with the C1, C2, C3 few auxiliary variables, and then you are making this kind of table. Now, can you solve once again this same thing, same problem? So again, the same method. Look, no, nothing other than this. That you are going to say F, T, U, W, R, O. Okay, and since these are the auxiliary variable, you also put them C1, C2, C3. Put their value 0 dot 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 9. I say you can write 0 dot 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 9. Okay, you start assigning something to F. Okay, and then yeah, you can start assigning anything to O. Okay, so what you can assign 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, any of the value. Assign 0, assign 0 over here. Then this value should be 0. By this you get 0, 0, 0. Then few more assignments. Since 0 has been assigned, nobody else can be assigned from remaining of them. You remove the 0. So 0, 0, 0, R becomes 0. This is a contradiction because R should be a different number. So you assign instead of 0, now you have to assign 1. Instead of 0, you have to assign 1. Then it come 2. Here is 1. Then what? C becomes 0. This C1 becomes 0. I think C1 need not to be different. Okay. Am I right? All diff is not applied on here. Okay. So it is 0. So it is no, there is no problem. Then you need WWU. So what to assign? Because 1 and 2 are gone. You can apply 3 to it. 3 and 3 is 6. So it becomes 6. U is 6, 3 and 3 and 6. So what is this? So 1, 1, 2 and 3, 3, 6 and here 1. So what you can get 1 over here, two numbers because t plus t should be 1. So it is not possible. Again, you go back. Instead of 1, you change something else and you keep doing this. So one solution that comes is 2, 3, 4, 2, 3, 4 is how much? 8, 6, 4, 0. This is one solution. And you can get another solution also that I would not tell. There are more solutions. So please try to find out them also. Is it right? So what is this assignment? F is equal to 0, T is equal to 2, and W is equal to 3, U is equal to 6, O is equal to 4, and R is equal to 8. This is what the assignment is. F is equal to 0. Okay. Okay. So right now we have seen that where these constraints were absolute constraints. Sometime it may be also be possible that these constraints are preference preference constraints. Means okay, I'm fine with this solution, but if it is, for example, when there is a bus, you are going somewhere, and let's assume what is the constraint? The first constraint is that everybody should be allocated a seat. Okay. So this is this is absolute constant that there should be there. But other constant could also be there that if two friends could sit nearby, I want to sit for example, on the window. Somebody want to sit on the back seats. So these things comes into the preferential constraints. When you are solving these things in constraints kind of problems, all the variables get the right value. This is called the node consistency. Okay. And then there is also a term that is called the R consistency, and you can relate it in your database systems. As you know, na, there is, for example, if there is a bank, so in every account, there should be at least the bank balance of less than 1000 rupees. But in complete bank, the assets of the bank should also be 1 lakh, 10 lakh, or something like that. So if you go to take the money out from your account, if you leave the balance of 1000 rupees, it would be allowed to you to take the money out. Okay, so this is called the node consistency. The R consistency is something, a bigger constant that is applied on the system, that says that you cannot, let's assume that your account has 5000 rupees, but total summation of the money in everybody's account becomes 10 lakh only. Now you cannot withdraw your money, because if you take it this, the this is the another constant that actually got violated, that the total assets of the bank actually going to be lesser than this. So this is the another constraints that can be implemented on the system. So our consistency algorithm is actually, this is our consistency algorithm that actually try to solve this particular problem. And again, this is not a very difficult thing to know. Only this constant propagation we are going to utilize. And this algorithm says what? That you remove, you take the first item and then revise, means for all other items you remove those things, and that as you've seen, when you have applied mm, blue color to one of them, so you remove the first one which has the highest constraints, and then you propagated this thing over here. Revise means for all other items you are going to revise their domain, and by this at the end you'd be able to find out the solution. This is the very simple algorithm. So all these things are simple. So here is another example of Sudoku. In the game of Sudoku, if you want to write that what are the constraints, how can you write? So do you know that how to find out the solution of the Sudoku? So this is a 9 by 9 grid where 3 by 3 grids are there. In every grid, there is a, all the numbers are 0 to 9. And this is what the solution is. I don't want to go into the solution, how to find out that. But I'm interested into writing out the equations that can specify this particular problem. So what is the situation? That in this particular line, what are the value A1, A2, A3, A4, A9? All of them should different. B1, B2, B9, all diff. All of them should be different. In one, if I write, it becomes A1, A2, A3, B1, B2, B3, C1, C2, C3, all diff. So you put more constant. So how many constant would be there? Can anybody tell me? Can anybody tell how many such constants would be there?
0 to 9.
So 9 into this particular direction, 9 such equations would be there. Similarly, in this particular direction, also 9 equations would be there.
So 9
9
into 9
plus
is 9
into
plus
9 plus 9 plus 9 for every square 9, 27 constants I have to write. Okay. So few minutes back, we have actually understood that we have to go to the backtracking road, means all the values are there. One by one, we can go and find out solutions. So there is one way that tells that, let's assume that, and essentially it is a kind of same thing that tells that, let's assume that A, B and C, three variables are there. Let's assume 3 and 4. These values they can take. Let's assume these values they can take. So what would you do? You would assign A is equal to 1, then B is equal to 2, then C is equal to 3. If it is not the solution, then C is equal to 4, C is equal to 5, C is equal to 6, whatever into the range 4, 5, 6. Then after that, if nothing is working, then you come, it become 3 over here. Then you assign 2 to this 1, 3, 2. And this kind of search is called backtracking search. Okay. So backtracking search is not that difficult to see. Everybody knows that. That one by one variable assignment, you are going to see that if the result is failure, then you it not failure, then you give the result. Otherwise, you get the next assignment and go back in this particular way that I just mentioned to you. Okay. So this is again one problem, and this is not a new problem for you. We have seen earlier also. This is what is this problem? 8 queens problem, where you want to put the 8 queens. So you see that. Let's assume that these are the positions. I'm not sure that whether you are able to see that where the. So one solution was that we have discussed earlier also. Let's assume that randomly I'm going to put like this, and then I'm going to do the local search. Local search means from here I see that if I take it forward, what is the problem? I think I'm not able to see this number. So it may be 2, it may be 1, it may be 3, it may be 2, it may be 1, it may be 2, it may be 2. So means what? That if I take it forward, how many places there is attack? So I say that 1 is the smaller number. So I can put this thing over here. Then I again pick any one other. Try to see that if I move it other places, how many places, how many number of conflicts are there. So again, I reduce I see that if I put it here, it becomes 0. So this is the solution now. If I put it here, then I get the solution. So this is how using back tracking and by reducing the number of conflicts, I can move into the forward direction. So one thing was this, that what I was doing, I was backtracking. In the backtracking, I was exploring everything. In the second method that I just discussed, actually uses one of the assignments, one of the variables, and changes this variable in such a way so that the number of conflicts, or number of places where there is a conflict, is getting reduced. And then you pick another variable, and by this it is supposed to do the things in lesser number of steps. Okay. So you want to minimize the conflicts. You can do the tabulation search sometime. As we have mentioned a few minutes back, that tabulation search is also a method that 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 is a kind of book where all the good moves are stored. So you can think that if you are into some particular situation that is there into the book, you follow next step according to the book. Another method that we have few minutes back seen, constraint weighting. Constraint weighting is this, that for all the variables, I'm going to change that particular thing that minimizes the number of conflicts. Okay. There is one more thing that is called the exploiting the problem structure. Hmm. So what it says, that let's assume that this is the problem. Hmm. And you divide the problem into n different parts. You say that I can solve the problem into and into by dividing the problem into sub problems. So let's assume that here C number of variables are there. How many variables are there? Let's assume total number of variables is n. Okay, total number of variables is n. And you say that you are dividing the problem in such a way, and let's assume that the perfect division is possible. And in every place there is C problem statements. So if the depth is, if you are going to explore the things to the d depth, so earlier you were needed because n to the power d, order of n to the power d items. But right now, if there are C, if your problem statement has only C variable, so you have to do this much exploration only. If total number of items were n, and each of them are going to have C, so these many number of parts would be there. So I can say that I can multiply this with the n by C also. I can say that this much number of complexity would be required. If I can divide the problem into smaller problems, once again, if I can divide the problem where earlier n items, instead of n treating with the n items, I only deal with the C items. And C is a fraction. C, how many such things would be needed? Instead of n variable, if I treat C variable, how many such things would be needed? N by C. N by C multiplied by d to the power C is the complexity that is I need to tackle with. So this is too less as compared to the n to the power d. If n variables are there, you are going to deal with the d to the power n complexity. But now your complexity is actually smaller. Am I right? So if you can divide the problem into independent subproblems, so your things could be faster. Another method is, there is one more method that actually talks about in, yeah, there is another method. For example, you want to find out the solution for this kind of situation. So here, if you structure the problem into the DAG format, you say that I would first assign the value to A, then I would propagate to the B. Whatever answer I have, I would propagate to the C. Then the B's value is propagated to D. Then it is propagated to E. Then I would propagate D's value to F. So you created this kind of directed acyclic graph, DAG graph. So here you created a linear way to proceed. So if you do like this, it would again be a better representation. Okay, can you see this, that it would take lesser amount of time to proceed, because here if you deal the things into the different order, so different kind of scenarios may arrive. But if you go into this particular way, we have seen earlier that any of the assignment, when you propagate, it solves your problem in a very in a big way. So this is again a very interesting idea that tells that you can create a DAG out of your assignments when constraints. So these lines actually means that D and F has some dependency, B and C has some dependency in terms of the variable assignments. So you convert this graph to this particular graph, and by this you are going to get the assignments. Okay. So this seems to be very good idea, but sometime it may be possible that the problem is not into this particular way that you can convert into this particular format. Hmm? In those scenarios, there is another method that tells that is called the tree decomposition of the constant satisfaction problem. And it actually says that can we club some of the variable and try to find out the solution? Very interesting idea. For example, in this particular case, if you find out the solution of only 3, okay, then can you use that to propagate into the solution of these 3? Can you then send this particular solution, whatever you got, to solve this particular problem? Only 3 variable assignment problem. So actually you are telling that I have small 3 variable assignment problems. And this is the independent problem. You are telling that I am going to first solve this particular problem, that's WANTSA. Then I would solve NTSAQ, this one. Then I would solve this particular problem. Then I would solve this particular problem. Then I would solve this particular problem. So all these problems are independently going to be solved. All these problems are independently going to be solved. And then their solutions are going to be sent to one place to another so that we can reduce the uh, number of computations. Okay. So when you are decomposing the problem into this particular way, every variable in original problem appears at least one of the subproblems. Two variables are connected by constraints in original problem, then they must appear together in at least one of the subproblem, so that at everywhere they should be solved. If a variable appear in the two subproblems in the tree, then it must appear in every subproblems along the path connecting to these subproblems. So this is easy to solve because you know that here the small problem is there. Instead of solving the complete problem, you are actually solving a smaller portion of problem. And by this, you can find out the solution of the complete problem. So that's all for today.